Hello and welcome to the New York City Category Theory Seminar, September 25th, 2024. Noah Chrein is talking today on a framework for infinity T-multicategories. So this is your third time speaking here.
Yes,
welcome
for
and
me.
thank you for doing this.
Okay, so I'm going to talk about a framework for infinity T-multicategories. So I want to say a little bit about the motivation as to why I'm doing this, because some of these things, I mean, they gel with some work that like Mike Schulman has done, but a lot of it kind of comes out of left field, and so I want to keep sort of a broader context as to, what I want to do. And, we were having some conversations about AI, and I don't want to this is not an AI talk, but some of these things, I think the end state is going to be for explainable AI. What I would like to do is I want to create let me get this straight. So what I want to do is I want to create a spatial framework. For doctrinally specified structures. Okay? And this spatial framework for doctrinally specified structures is what I think is going to act as a more structured latent space to store concepts in machine learning. So instead of a vector space, it would be something much more higher structure that keeps track of the structure of the entities in which a learning algorithm might work with. So this is like this grand goal. I'm not anywhere close to this. So this is kind of the last thing that I'm going to say about this. But in categorical terms, so like a categorical goal, and this isn't necessarily my goal, I feel as though this is the goal of formal category theory in general, is a framework for N theories. So an N theory is a theory of structural specification. And I'll get a little bit more into this concretely, because this is not actually what I'm presenting here, but this is sort of an end goal of what I'm trying to work on. So an intermediate step for a framework for N theories, so I'll say a bit more about that later, but an intermediate goal for a framework for N theories, and this is what I will be presenting. So this intermediate goal is to make a theory of schemas. So schemas, as I'll say a bit more of, sorry, someone just called me. This theory of schemas, which I'll say a bit more of in a bit, like schemas encode the axioms of a mathematical structure. So I want to make a theory of schemas, the virtual equipments, schematic. So there's this common phrase in category theory, which I think I don't know where I heard it first, but that category theory eats itself. That you can use categories to define the structures in categories that are used to define the structures in categories, etc.
It's its own meta theory.
It's its own meta theory, exactly. Exactly. So I think that one of the ways to get at a framework for N theories, so N theories in some broader sense are like higher order categories that encode the structure of lower order categories that encode the structure of even lower order categories. So a first step to this sort of iterated structural specification would be to make virtual equipments into something that is categorically specified. So when I say schematic, I mean that there is some category and some schema by which the schema is encoding the structure of that object or category in general. Okay, so that's what I'm going to present here. I'm going to present a schematization of virtual equipments. We'll see how far I get. I'll at least give a schematization, I haven't come up with a good word for that yet, of virtual double categories.
Just on pronunciation, is it schemas? I thought it's schemas.
Yeah, some people say schemas. I like schemas.
Tomatoes.
I don't really know.
But you said schematic.
Schematic? Okay, well, I'm flip-flopping on it. You know, don't hold me at the polls.
Some say schema, some say schema.
Yeah.
Tomato.
Tomato.
Yeah.
Tomato.
Yeah, so, okay, schema, schematic, either way, a schema or a schema is a means of encoding the axioms of a mathematical structure. So I think I'll probably say that 1,000 times to this talk, so.
But I assume at some point you will give a definition.
So okay, let me get through the talk. So, I mean, that actually is a good question. There are attempts at definitions for schemas and doctrines, and they're all like, you know, choose a certain structure, usually a category, but I think that the theory of schemas and doctrines is much larger than category theory, maybe, in general. But I don't...
Well, I'm saying more modified, like this is a definition that works for what I'm doing.
Yeah.
Not
so
saying that you would have an ultimate definition, just.
So this is all still the motivation for what I'm going to show.
Oh.
So I'm not going to give a definition of schema or.
This is not okay. This is just all at the point is all motivation.
Yeah, this is all still motivation.
Okay.
The reason why I want to make virtual double categories schematic is to make like a theory of schemas schematic.
So notice if I ignore this blackboard, I'll be safe from now on.
No, you won't be safe. Okay, you might be safe, but this I think it's good to keep in mind that this whole work is about structural specification via schemas.
Right, but you're talking about goals. This is not. Technically, I don't need to know any of the terms here to follow.
Let me keep through with it, and then you can ask more questions, yeah. Okay. All right, so there's two things that I'm talking about here. So there's a schema. A schema, this encodes axioms. And this typically looks like a category, but it need not be. It can be something else. And a doctrine is going to interpret schemas into collections of structures with the axioms of a certain schema. So I'm going to give you some examples, and I just want to say, like, I'm not like sticking to the fact that a schema is a type of category or a doctrine is a type of category, because I feel like that claim is actually too strong. But the examples that I'm going to give you of schemas and doctrines are all categories of some sort. So here's one example, and hopefully you've seen this before. The simplex category. So the simplex category, which is a category, this is the typing symbol, so simplex of type category. So this encodes the axioms of simplicial sets. So the doctrine, in this case, is cat, the category of categories. And the way that we turn axioms into a collection of structures is by looking at the presheaves on delta. Yeah? So there's plenty of other examples. So there's the monoid schema. So this is the schema that encodes the axioms of monoids. And if we look at monoidal category functors from delta plus into set, we're going to get our classical set-based monoids. Okay? And
the monoidal structure on set is just product.
Yeah, so, right. I'm sorry, my notes are on my phone. I'm kind of struggling to get into my phone right now. Yeah, so the...
there's a word you didn't use, is sketch. A schema is a generalization of a sketch?
So...
Which is a generalization of an algebraic theory?
Yes, exactly. So that's a great way to think of it. They're all in the same class. So I use schema like super broadly. You know, like sketch has a definition.
Right.
It has a definition as a sort of category, and algebraic theory likewise. And there's even more, you know, like restrictions on algebraic theory. But in my view of what a schema and a doctrine is, it's just something that encodes axioms and then something that interprets the axioms that are encoded into structures. Mm-hmm. Okay, so this doesn't need to look like categories, but I am giving you a bunch of categories as an example, because it's kind of hard to find other examples. So one last example, and I'm bringing all three of these up because I'm going to use all three of them. So we have the monad schema. So the monad schema is a 2 category, and the functors from the monad schema into the 2 category of categories are monads in categories. Okay, so a monad on a category. If you haven't seen a monad before, a monad has this following structure. So we have a category C, another, so the same category. We have the identity functor, we have a functor T, and we have a functor T squared. And we have like a multiplication map, mu, and we have like a unit map, I. But this talk is not about monads, so I'll just leave it at that. The idea is that this schema has this shape, and so functors from this schema into cat are things of this shape. And that's the case for all of these. This has the shape of simplicial sets, this has the shape of monoids, and so functors into the right place are going to give us the structures that we want.
So another way, like especially with that last one, would be that, at least with these examples, and there's going to be others that aren't like this, but the last one especially, that looks like sort of a version of a theory of classifying objects or classifying spaces as well.
Yeah.
Right, where the maps into something, you have a structure, and the universal structure, and then the maps from it pick out all the copies within some category in this case.
Right, right. This is actually almost more direct than like a universal property. This is like I'm listing the axioms here, and like I'm instantiating them in the place I want them to be.
Right, no, I just mean it's like a classifying space for a group.
Yeah, of course, of course. Yeah, they're highly related for sure. But I'm actually not talking about the exact relation in that case. So I want to make a distinction, which I've said in words, is that like schemas are not always categories. So if you look at these examples, like, yeah, I've given you like flavor of category, but the only actual category I've given you is the simplex one. So this should have a monoid here. This is a structured category. This is a higher category. So we don't necessarily know, what counts as a category, as something that is some flavor of structured category. So that's why I'm trying to leave this open-ended. Even though all the examples so far look like categories, you know, there's no like unifying definition of what some sort of structured higher category is. There's things that fall out of that purview and things that fall into it, and I think that really all of them can still encode axioms in a certain way. And on the flip side, like not all categories are schemas. So, you know, I want to distinguish things like the category of open sets on a topological space. I want to distinguish that from these schemas, because the presheaves on the category of open sets is really like trying to glue together data on the open set. So this is not encoding the axioms of some mathematical structure. But on the other hand, here, each of the objects in the simplex category refers to a different level of coherence data of simplicial sets. So these are the axioms of the structure of simplicial sets. So I want to call these presheaf categories. You know, sheaf is really reserved for like gluing together data, at least in my opinion. So I want to like distinguish categories that are encoded, or structures that are encoded by a schema as like schematic.
Okay, so point said that's more about how you think about it.
It's more how you think about it.
Technically,
yeah.
I mean, they're the same, and it could very well be a topological space happens to be, you know, by thing happens to be isomorphic to delta.
Yeah. Yeah. So yeah, you're right. So
it's not that there's, you know, some technical condition on the category it's being posed, it's more what I'm doing with it.
Right, so if we had a general definition of schema, I would think that it would, you know, carve this from the general ones. It might be, like you said, it might be the case that X gives you the simplex category. I don't know what topological space would do that, but maybe just like literally the simplex might do that, but no, it wouldn't. But anyway, like, right. So I'm trying to distinguish.
You don't have any such, but at the moment, you don't have any such technical criteria.
No. And I think that like a solution for a definition of schema and doctrine in like a general sense, that would be the framework for end theories that I think people are looking for. And you know, okay, maybe I shouldn't say too many hot takes. But I do think that like this framework for end theories is like the goal of category theory in general. But you know, that aside, so I think at this point I can kind of move away from schemas and doctrines. I just wanted to get this in your mind that this is like, you know, what this is all about. So I want to like describe to you a actual definition of a doctrine. This is a more classical definition. So a yoneda structure. So this is like a classical definition of a doctrine. And there are many definitions of a doctrine. I'm not claiming that this is the one. But this is, I think, the first setting in which I heard the word doctrine. And so a yoneda structure, I'm not going to get too far into this, is 2 category K. So we have a 2 category K. And this 2 category K has like an abstract presheaf thing. So this is like abstract presheaves. Presheaves on A.
Wait, what's A?
So A is just an object.
In K.
Yeah, I'll write it like
Okay.
this. So A is an object in K.
Yeah.
Yes, thank you. And so yoneda structure, we can create this abstract object of presheaves. So yeah, this is also in K. And we have a abstract yoneda embedding. So So this all is going to act the same way that it does in cat with the actual category of presheaves. And it has like a yoneda lemma, which has the form of a left extension. So, you know, all this stuff, if you've heard about it, that's great. This is, I think, just setting the scene for the next step here. So I guess I'm doing a lot of scene setting, but it's probably necessary. So this is what replaces the yoneda lemma. And when I say a left extension, this means that we have some isomorphisms. So we have an isomorphism like this, which you can ask me to explain more, but I just want to show you that this abstracts the yoneda lemma. So on the right here, we have like a representable functor. So B is, you can think of as a category inside of the collection of two categories. So we have our representable functor into some other functor. And then we have that F plugged into G, which is reflective of the classic yoneda lemma, like the one category yoneda lemma.
Well, what is I? BFI?
That's a one. So one just means like this is a functor, and if I plug something in, it goes into this term here.
Okay.
Yeah. So right, like BF1 is going to be it's something called a profunctor, which I'll actually talk about more. And this is going to be B cross A up. Just hoping I'm getting the direction right here. To set, well, in the classical case, so assuming that this is a category, this is what this would look like. And so if I plug things into this, I should get, okay, yes, I did do it opposite. Yeah, so.
B up A?
Yeah, I'll just swap these. This is the thing that I do all the time. So FA, B. So, you know, so that's what that BF1 stands for.
Yeah, okay.
Okay. So, I want to call into question a number of the things. Okay. All right, maybe I think I actually will leave this part out because I've done enough motivation at this point. Okay. All right. So this is, you can see how this is like a doctrine in the sense that like the primary example is going to be the actual presheaves on categories. So like P of something in the classical case, so in like the case where K is the two category of categories, we have the actual like presheave functor. So if I plug something in, I get presheaves on that thing. And right, so like I want to say a number of things that are wrong, or not wrong, but limited about this construction in terms of structural specification. So I've shown you, three different examples here of something that encodes axioms, and then something larger that can handle that encoding of axioms in a certain way. So there are a number of things that are limiting about this. So the first thing is that cat is not enough. So we might want to use like fiber categories. I mean, I'm a category theorist, so all these things are going to be categories as example, but we might want to use fiber categories, or we want to use monads instead of cat, and I think this list is probably uncountably infinite, of different paradigms by which we can interpret schemas. Set is not enough, and the entire field of higher category theory is essentially the fact that set is not enough. Okay, so we might want this to be like infinity groupoids, or we might want to do something more algebraic, like we might want this to be vector spaces or some sort of algebra. Okay, so 3, and this is kind of my claim, is that like Hom functors, so the Hom here, this is what I'm referring to as Hom, like Hom is not enough. And like when we're talking about specifying structures, like if any of you are programmers, like any programming language will tell you how to specify structures within that programming language. How do I spell programming? Programming languages. And like, some functional programming languages are explicitly categorical, but like Python isn't explicitly categorical, and yet I can do like, define a certain class and then list its features, list the requirements that I need. So, Python should also be a doctrine, not just categories. All right, and 4, which finally, this is like, what I'm talking about in this talk, is that this notion of doctrine is not iterated. So what I mean by that is like categories, right? So this is a doctrine. It's an example of a yoneda structure. So categories with its pre-sheaves is a type of doctrine. But of course, via like the nerve operation, categories are going to embed, small categories at least, into simplicial sets, right? So categories become quasi-categories, and if you remove all the extra structure, they're just simplicial sets. And like this is schematic. So we have a doctrine whose structure is specified by some higher doctrine. Meaning that like this should be like a zero doctrine, or we start at 2 when we talk about N theories. This is a doctrine, and this is like a 1 doctrine. This is a 0 doctrine. This is a 1 doctrine. And sorry, I'm pointing to the wrong thing here. Let me erase this and rewrite this. So we have a doctrine whose structure is specified by a schema which is interpreted by another doctrine. And they're both cat here, just to be a bit more simple, but like don't let that worry you. This is like a 0 doctrine, and this is like a 0 plus 1 doctrine. So it's a higher level up of doctrine. So the structure by which cat uses to interpret schemas, which encode axioms, the structure by which cat uses to interpret schemas is encoded by a schema.
Right.
So this is what I mean by like iteration of doctrines. There should be levels and levels and levels of doctrines. This is also what I mean by N theory. Levels and levels and levels of theory by which the ability to encode and interpret structure like passes over to its lower level. Okay, so this is sort of the like conceptual starting point as to like why I'm motivated to do what I'm about to show you. And so what I'm about to show you is an attempt to, or it's like a first step at an attempt at defining what a like a good, robust notion of iterated doctrine would be. Okay. So what we're going to do, very concretely now, so like this was all quite abstract, though there were some examples, but this is much more concrete, is what we're going to do is we're going to find a schema, which we'll call delta M, which is going to encode the structure of multicategories. Okay? So why I want to encode the structure of multicategories is because virtual double categories are also a form of doctrine. And I'll say more about this, so if you don't know what this is, that's fine. But this is a form of doctrine. And so what we're trying to do is we're trying to make a doctrine schematic. We're trying to encode the axioms of a virtual double category in a schema that there's some higher doctrine that interprets those axioms. And when it interprets those axioms, we exactly get virtual double categories. Okay. All right. Am I losing you all?
No.
Okay. All right.
You have to tell us what a virtual double.
Yes, I will. I will. Okay, so let me start actually with an example. So the quintessential example of a virtual double category, which I'll just write as a VDC. So an example VDC is the virtual double category of pro-functors. Okay, so like I wrote over here, I didn't really mean to bring this pro-functor stuff up this early. However, a pro-functor is exactly this. We have a functor from A op cross B to set. Okay? And this is, you can think of like an abstraction of the Hom functor. When A and B are the same, so A op cross A, the Hom functor is a pro-functor. The Hom functor like, is the quintessential pro-functor. And what we want to do, the trick of virtual double categories, which makes them so much easier to work with than, say, yoneda structures, is that we can think of pro-functors as just a different kind of morphism. So we have like a specific kind of morphism, which is quite structured, and we change this into like just a different dimension of morphism. So I'll tell you how this all comes together in a virtual double category. So a virtual double category has 4 levels of structure. So the first level are objects. The second level are morphisms between objects. The third level are promorphisms between objects. So we have objects and morphisms, and we have objects and promorphisms. So 2 different dimensions of morphism. That's where the double category comes from. But where the virtual part comes from is that the cells are not from one promorphism to another, but rather from a path of promorphisms to another. So this would be like P1 down to Pn to like Q. So we have a bunch of promorphisms all chained together. And we have something like a natural transformation down to another promorphism, a single one. Okay.
And the vertical arrows are functors?
So this is an abstract picture. In Prof, these would be certain types of natural transformations.
The two side ones.
Oh yeah, these ones are functors, yes, in proof. Yes, exactly. Okay. All right. So anytime you have a morphism from a collection, whatever collection means, a collection of things to a single thing, this is what multicategories are used for. Generalized multicategories are used for, where the domain has multiple things and the codomain has one thing. So a virtual double category is a kind of multicategory. But before I get into that, I want to give you some new notation, which allows us to work with these cells, which can get quite cumbersome if I want to write compositions of these cells. I'm going to do it, and you're going to see how big it gets after just level 2, let alone level n. So this new notation, what this does is a single promorphism is going to just be like an arrow with a notch. This is, I haven't changed anything yet. A path of promorphisms, instead of drawing a path like ... I'm going to draw it as a path with 2 notches. Okay, simple. Path of paths is just going to be 3 notches. And so on. So I can, instead of drawing n notches, I can just write n here.
Okay, so the point is you make when you put, let's say, 2 paths, so you still distinguish, you don't just combine them into one long path, you keep the keep track that they were 3 separate paths and so on.
Yes, you want to keep that data. That's essential to keep that data, actually. So, and that's what makes working with virtual double categories on a practical level so difficult, which is why this notation comes in handy. So let me just draw you what a composition of cells would look like.
I just want to make sure I understand correctly your definition.
Yeah, no, absolutely, you got it right. So in order to compose cells, I need to have a bunch of cells up top. So I have, instead of a path of promorphisms, now I have a path of cells. And then underneath it, I have a single cell. So if you've worked with multicategories, it somewhat looks the same. You know, like in multicategories, it might look like I think these are called dendroidal sets. But this talk is not about that. So.
Well, but basically, it's again some kind of tree-type composition where I go from n to 1.
Yeah, exactly. But see, the thing is
it may have different rules, but it is that type of composition.
Exactly. So a generalized T-multicategory, which I'll define for you in a second, that's due to Leinster, gets what you said, going from n to 1, to work for different notions of collection of things. So in this case, we're talking about paths instead of just discrete entities.
Sure.
So if I look at this composition, I mean, you can imagine if I, threw even another composition on top, how cumbersome that would be. This composition of cells in the new notation becomes simply like this. So I still have to draw cells, but now I'm going to have a path of paths, a path, and then a single edge.
Yeah.
Right? Okay. And more so, if I look at this from the side, if I turn this to the side, and I use now squiggly brackets, so I call this top one A, the second one B, and the second one C, or the third one C. So A is a path of paths, and then I have a cell that goes to B, which is a path, which goes to C, which is a like a single object, then you can imagine that the composition is going to look something like this.
All right, so you're using the same notation corresponding to the number of slashes you have an arrow is the number of brackets you write around the letter.
Yes, exactly, exactly. And the point here is that once you do this simplification and you look at it from the side view, you can see that this is basically a simplex. You know, there's a lot of extra structure attached to all these things, but if you squint your eyes hard enough, it's a simplex. And so what we're going to do is we're going to use the definition, which I'll bring up in a second, the definition of T-multicategories, and the process of turning categories into simplicial sets. We're going to take those two things and combine them, and we're going to turn multicategories into a certain kind of pre-sheaf on this schema. So I'll just write what I just said. We're going to combine the definition of T-multicategories plus the process of going from cat to simplicial sets to get a type of schema that will look something like this. Okay, and I'll make this much more well-defined.
Who is T now? Who is T? Because instead of
T is the, okay, yes, thank you. I've been saying T-multicategory, and I'll define it now.
So T just means, instead of going to say, you go into this T-multicategory.
Yeah, exactly. So T is a monad, and I'm going to write this right now, so this will be the answer to your question. So let T, actually I'll draw the category underneath it as well. So let T, acting on a category E, be a monad. And again, if you haven't seen monads, or at least you haven't seen like the categorical view of monads, they are, it's a functor like this with a unit morphism and a multiplication morphism. So we have a monad. So we have a monad acting on a category E. And what we want to define are T-multicategories. So define a T-multicategory as follows. So, okay, let me get like an audience opinion on this. So the definition of a T-multicategory is a bit complicated, and we can go through it. Well, we are going to go through it. But have you seen the definition of a category in terms of like it's composable? Like, okay, let me just do it then. Okay, so before I give you the definition of a T-multicategory, let me just show you what a category looks like, a regular category. So we have an object of morphisms, we have an object of objects, and we have two face maps, the domain and codomain, and then we're going to have like composable maps. So we have something like this.
The internal view of categories.
Yes,
Yeah, this is an
thank
internal
you.
category.
That is the word I was looking for. Yes. So this is what it looks like for categories. So T-multicategories are a generalization of this. So it's a bigger diagram, so just bear with me. Let me write it out and make sure I get everything correct. So
technically that's the sketch of category, because to get the top thing you need a pullback.
Right. And that's like sort of the glory of simplicial sets is, and I guess I say this now because it's a good answer to this question or this comment, is that when we do simplicial sets, like when we're going from categories to simplicial sets, we forget that we need a pullback. And we just have an object that witnesses the compositional morphisms, or the, composable morphisms. Okay. So, all right, I kind of did this backwards, but it's fine. Like, so this is the process of changing categories into simplicial sets, okay? And what we're going to do is we're going to do the same thing for T-multicategories, okay? So here's a T-multicategory. This is the most important part of this kind of big diagram I'll draw. So we're going to have, so we'll have an object of objects, and all these things are in the category E. So again, let T be a monad that's acting on E. We're going to have an object of objects, an object of morphisms, but its domain is going to go to T acting on the object of objects. Okay? So if T, for example, if T is the free category monad, or the path monad, I'll just use the word path. If T is the path monad, then this is going to be paths of promorphisms, like this. So the morphism is going to be like the cell.
Nice.
The domain is going to be a path of promorphisms, and the codomain is going to be a single promorphism.
So,
Got it.
in this case, I would call the T alternately, and these are both lies, but whatever, the terminology is you could think of it as either a multiplicity or a container.
Yeah, sure. Right.
Right, and so in particular, so we have monad, if you have T to the n, that's what all the n brackets or the n ticks on the arrow or
So this is specialized that T is the identity monad. You're going to get back to
exactly.
cat, and then,
exactly.
Yeah.
So an identity multicategory, an ID multicategory is just a category. An FC multicategory, which I don't know if I wrote over here, is going to be a virtual double category.
Okay.
I'll say that again. But I didn't finish with this diagram.
Sure, right. You gotta
Because we need to take care of composable morphisms, etc. So, so like, now this second, like the thing that we want to compose with is not just a morphism, it's a path of morphisms now, a path of cells. And it's like codomain is not just going to be a path of edges, a path of promorphisms, it's going to be a path of paths of promorphism. Yeah? So here we go. And the composable, it works exactly just the same. The composable cells, or the pairs of composable cells, is again just a pullback. Like this all just goes right through. And if you want to like look this up, this is, I hope I'm spelling this right and saying it right. Leinster's higher operads.
Yep. Yes.
So you can check this whole thing there.
In fact, I happened to, with two other people in this room, looked at it about half a year ago.
Okay, good. Yeah, great.
So
That's very
the
true.
diagram looks quite familiar. Yeah.
Right. So the only issue with this, or the only thing that makes this kind of difficult, is that when you compose these two things, what you want is not not a map from a path of paths into a single path. So that's not what you want. What you want is a map from paths, like a path, into a single path. And so what we need to do is we need to intercept what's going on here with the monad multiplication. So for example, with the path monad, it will take a path of paths and just concatenate it, Okay. All right, so on this side, I'll intercept it with the identity function. And
I'm just going to observe one thing here.
Yeah.
That what this is sort of saying is that we actually have two different notions of composition we're making use of. One notion of composition arises from the multiplication of the monad, and one arises from our multiplication object.
So I wouldn't call this composition, because specifically, like this is called a virtual double category.
Yeah.
And so, like there are no like a priori ways of composing these things. Sometimes you can, but like when I give you just the definition of a virtual double category, you're not composing these. All we're doing with this multiplication, the mu, so the mu is going to take a path of paths, and forget these inner brackets.
Right, so that's what I'm saying, is you can
Oh,
compose
I
a
see what
path
you're
of
saying.
paths into a path, that's what
Or
I
if you
mean.
leave out the word.
I get
You've
it.
got virtual composition,
Yeah.
that's what I mean, you've got virtual composition, or purely formal composition induced by the monad.
Right, sure. Yeah, I definitely shirk at saying, like, calling this mu composition.
Well, it's let's just call it an operation.
Yeah.
Yeah.
Say we have
I
two
don't know.
operations, and
Right, but, well, I mean, like, there's definitely a composition of cells, so you are composing, like, this level with this level, but you're not composing these paths. You're just, I would just call it multiplication. I don't know.
It's
I mean,
fine,
yeah,
yeah.
whatever. It's it doesn't matter that much. Okay, but yeah, good. I'm glad you guys get it. Okay. All right, so I'm going to rearrange this diagram and make it more conducive, more like neat, looking like this. So when I draw it like this, it's to show you what's going on.
Yeah.
We have a domain and a
Right.
codomain, and we have a composition. That's all that matters in this diagram. So the way that I'll write it now kind of obfuscates the ideas, but it's going to make it easier to make it schematic. So I'll write it this way. So here we still have our M1, and we still have like our M0 and our domain, our codomain, and here we'll have T of M0, and we'll have T of M1, and this has all the things that you need it to have, T squared of M0, and here's our multiplication map. And now instead of writing like the composable pairs, I'm going to just have an object that witnesses composition. Okay? So I'm replacing the composable pairs the same way that I replaced composable pairs in categories and replaced them with witnesses for composition. Here I'm replacing composable cells and replacing them with witnesses for composition.
Is that what the M1 is on the bottom, basically? You have the line from TM1 cross M1 to M1, right?
Yes.
Would the M1 on the bottom be the witness in this case?
No, so let me draw from a side view. So here, like I had before over here, this, like if I was talking about regular composition, I would write something like this. I mean, this is wrong what I'm writing, but it'll give you the idea. Like G of F and like equals, right? So I have, a bunch of these cells on top. That's what the G is supposed to represent. I have one cell. That's what the F is supposed to represent. And then I literally compose it. It's an operation. I plug these two things into the composition operation, and I get G of F, right? But so what I'm replacing this with is like a simplex. So instead of G of F, so I'll have still G and F, I'll have an H down here, and I'll have a simplex that witnesses the composition of these two things. So from the view over here, let me give this guy a little bit of an angle. This would not just be a composable pair, but rather it would be an entire like two-dimensional thing. Okay.
Right, the filler of the 2D thing is going to be, is the action.
Yes, exactly. Okay, I got to the end of the board here. I guess I'm writing really big, but okay.
Perfect.
Let's see, how much time I got? It's about 30 minutes, or a little bit less.
also discuss at the beginning where none of us are in a rush.
Okay, well, either way, I think there's definitely some stopping points I can make before I get total. I mean, I actually have so much content. So, but there's some good stopping points. So whenever you guys are, feeling fatigued.
What we've got now is we've got your multicats. You've given us a nice version of T-multicats.
Yes.
So yeah, so just I think take us to your definition, your proposed candidate definition of a schema for them, and then that's a really feeling place to be.
I think so. Yeah. Okay. So let me erase all this stuff over here. All right. So. Okay, let me try to squeeze this in all the way here. Sorry. So what we're going to extract from this diagram, so this is our definition of T-multicategories. This is the classical definition. This is the new diagram where we're creating witnesses for composition. And now this is going to be a portion of the schema. So now instead of having...
So this is new diagram analogous to what you did with the original category, where you just put a C2 in for, instead of going into details that had a pullback, etc.
Yeah,
Okay.
exactly. So now I'm going to, let's say, what's the right word? I don't know if abstract's the right word, but I'm going to take away the detail of these M's here and have something that captures the axioms which this diagram is supposed to represent. So when I say axioms, I mean like we have objects, morphisms, we have relations between the objects and morphisms, and we have witnesses. So, that's what I'm saying are axioms. They're like coherence data is another word for it. So I'm going to now create like a generic is the word, schema for this shape of diagram. So this is a portion of it. So, just like for the simplex category, which I'll bring back up in a second, but just like for the simplex category, the objects of this are going to be basically just numbers, so pairs of numbers, like a number above and a number below. So this one is going to represent M2. This one is going to represent M1. This one will represent M0, and then I'll have some more. So as I go to the right, I'm increasing the top number. So yeah, I'll just write it all out and then I'll talk about it.
Right, so you're just writing down the how many exponent, the superscript on the T and the subscript on the M.
Yeah.
So not have to write T and M 500 times.
Yeah, exactly. Yeah. So, like you just said, the top number represents the number of applications of T. So T squared or just T, and also it can go all the way up to R. And the bottom number represents like the dimension of cell that we're talking about. So 0 cell or object, 1 cell, morphism, 2 cell, witness for composition, 3 cell would be like a witness for associativity, etc. Okay. So, okay, now I'm committing over here. So in general, delta M is going to have this shape. So it's going to be Rn. So R is going to refer to the number of times we are applying a monad, and N is going to refer to the dimension of cell. We're going to have face maps. So face maps for I less than N. If you've worked with simplicial sets, you know that there are F0 all the way to Fn. So here, only the face maps that are less than n are going to go straight down to Rn minus 1. And sorry, this should be going up. We'll have degeneracy maps. And this is going to be talking about like identities of these cells. And we'll also have like the morphisms that come from the monad. So like this is multiplication. I should say like this is all kind of in the opposite category because we want this to be, we want to think about pre-sheaves on this eventually. So the multiplication is going upwards instead of downwards. Like typically when you talk about a monad, it goes from like t squared to t1, the multiplication. We're going the opposite direction because we're going to be talking about pre-sheaves. It's just one of these unfortunate things about, you know, the yoneda lemma.
Face, co-face, degenerate.
Yeah, yeah. And there's one other map, which is fn. So we have fi less than n. This doesn't increase the amount of times we apply r, but fn will. And so I wanted to give you like a nice synthetic definition of this delta m, but it's going to require a bit of a, like, I think it's going to require a bit of explanation about shape categories in general. So let's see if I can somehow get around that, because I think that's going to make the talk super long. Yeah. I think that this is what people are going to get out of this talk, so I'll just do it.
Let me check one thing. So just since, in terms of next boards, what we've done is your delta m is a category schema in this sense.
Yeah.
And then presumably all the business about the e and m1 is going to go over into the doctrine when we interpret it somehow. In order to get, is that correct?
Yeah, yeah. So maybe I'll just write what you said, and then we'll see how far I get with the shape category stuff. Because, you know, the way that I just wrote this here, like this is not a definition of delta m. And this is also, even if it was, it would be like a highly combinatorial one where I'm just enumerating things. Which, yeah, it is fine, but it's hard to work with, you know? So, like, the reason, like, delta is really easy to work with is that it's also, like, the category of finite order-preserving sets and maps. So, like, we do want something that looks like this. Unfortunately, it's not so neat, but there is something. But what I will say is that, like, once we have delta, so there is a monad on delta, or there's a monad on delta A. Okay, which is just given by +1, meaning we send Rn to R plus 1 n. And all of the like monad morphisms, because we need an I and a mu, come formally from the I and the mu that we've supplied. So there's a monad on delta m, which perhaps I'll get more into if I feel like, you know, I can do it in a reasonable amount of time. But I want to get to the punchline here, is that a T simplicial object is a monad preserving functor from delta m up into T. So we have this +1 monad, and this functor needs to preserve that +1 monad. So I'll call this V, or let me give it about here. So a functor, monad preserving functor on delta m is going to be a T simplicial object, which is like sort of a simplicial, as simplicial sets are to categories, T simplicial objects are to T multicategories.
Nice.
Okay. So let me write this a bit more contextually aware. Like, you know, what does this all belong to? So first of all, I should say that the category of monads, which I actually already wrote over here, so the category of monads, the two category of monads, are the two functors, so the morphisms in 2cat from the walking monad, or the monad schema, into the two category of categories. And so the category of T simplicial objects, which I'll just call T-ob, is going to be the monad preserving functors. So this is going to look something like this. So this is the category of monads, and so the monad preserving functors are then the functors within this two categories. So when I look at the functors from this schema into cat, this whole thing becomes a two category. This whole thing becomes a two category, and so I can consider functors now from certain monads. So delta m up with the +1 monad into T. Okay, so the category of T objects is this formal construction at this point. So we want to step from these T simplicial objects to T multicategories, right? And so what we're going to need to do is we're going to need to do the same thing that we do to get from simplicial sets to quasi-categories. So I don't know if you've seen this before, you must have, this room has a lot of experience. So like a simplicial set sigma is a quasi-category if the map into the one-point simplicial set, so this is a terminal map, lifts against these things called the inner horns. And so what I mean is lift is if we have any diagram that looks like this. So this is a diagram of morphisms of simplicial sets. So this is going to essentially pick out n-composable morphisms, and if I lift it, meaning that there's a map here that completes this square, this is going to be finding the composition of those morphisms. So solving this lifting problem for simplicial sets, we have n-composable morphisms, and then a solution to those n-composable morphisms. Mm-hmm. So this property is what makes a simplicial set into a quasi-category. So this is S-sets, how we get to infinity categories or quasi-categories. Mm-hmm. And so we want to do the same thing for these T objects. Okay, so what do we need to do that? Well, one, we need something like a representable T object. So we need something like this, okay, to replace the representable simplex. And then we also need something like a yoneda lemma.
No longer a horn.
Yeah, we also need the horns, but that'll come later. We need a yoneda lemma because this yoneda lemma is like a sanity check, in the sense that, for example, if we look at the yoneda lemma for simplicial sets, so representable, the maps from the representable simplex into sigma, the yoneda lemma tells us that this gives us the n simplices. And so when we're talking about maps from the n simplex into sigma, we want to know that we're actually getting you know, the n simplices, right? So we need a representable, and then we need something that looks like the yoneda lemma, so we need something that looks like this. So I'm putting just square brackets because there's some things that go wrong, and I will talk about them. But what we want is something that looks like this. So we take a representable, and we look at maps into like an arbitrary monad preserving map, so a T simplicial object, and we would want this to be isomorphic to plugging in Rn to B. Okay, so let's see what we can do. Right. So I want to enumerate a number of problems with this. Okay. So first of all, I actually just erased it, but like cat. So the monads on categories is not a yoneda structure.
What fails?
There is no yoneda embedding, because if you like try to op something, you go from monads to comonads. So you know, as soon as you do an op, you land in a different universe. So you know, there's not something like this. There won't be a delta m delta m into this whole big thing. So that doesn't work. Like just an X. Okay. However, there is like cat is a yoneda structure. So maybe we can use something with that. However, if we go down that route, so say we do something like that, we have cat from delta m, so we're forgetting now the monad. And we go from some representable, so we want something that looks like this, into some T object. So cat is a category. This whole thing is also a category, but this thing is a set. These are sets of morphisms.
Right.
And so we definitely can't have it be isomorphic to VRN, which is an object of E. Okay, so what we're going to have to do is enrich delta m. Okay, and we'll just work with delta m off. And luckily for us, the thing that we care about, or the monad that we care about, is the graph monad, or sorry, the free category monad on graphs. And graph is a pre-sheaf category. It's schema, or it's sketch even. I think it's so small that it could probably be many things. But the thing that encodes its axioms is a pre-sheaf category. And so we actually have a change of base that we can use. And let me get this, I want to get this one right on the first shot instead of fumbling. So let me get this up. So for a pre-sheaf category, among other things, I mean, other things will work, we can do a change of enrichment base. So, I mean, this is like really the dumbest thing to do, but it works. Where it's like, okay, we start with a monad, so that's a functor, a two functor from delta plus to cat, and then we hit it with the change of base. So the change of base is essentially like we take all the homs in here, which are sets, because they're categories, and we just like multiply it by the unit graph. So we're not really adding any data. We're turning a set into like discrete graphs, is essentially what we're doing. So we're really not doing anything. All we're doing is making sure that we land in the right universe.
Mm-hmm.
That's it. We haven't changed any data, really, by doing this.
Gotcha.
Yes, you want to interpret them as things, not
Yeah.
just plain.
Not just as sets, exactly.
So this works for graph or anything else generated in this way?
Yeah, yeah. So what, I mean, I forgot exactly what the conditions are.
Mm-hmm.
But the conditions are quite loose, and I'm pretty sure it only has to do with like the existence of this monoidal unit. Or maybe it has to do with the monoidal unit being representable. Whatever, it works for graphs, yeah. And maybe I'm just actually being a stickler and there's really no conditions and it just always works, but it works for graphs, that's all I'll say.
Sure.
That's all I will claim. Okay. Okay. So now at least we've sort of figured out this one in the case that now we're working with E categories. And so the representables that we're searching for, at least this functor category is going to be in E as an enriched category. Okay. And so now we can look at the enriched yoneda lemma. So the enriched yoneda. Okay, and by the way, I always suggest Kelly's book on enriched category theory. It's like the only reference that is just so streamlined for enriched category theory. So the enriched yoneda lemma in this case is going to say it as follows. So we'll have E cat from delta M op E between now this representable functor, which I'm no longer going to write in this form because we don't necessarily have this, although it's kind of obvious what it's going to be. It's going to be the representable functor. So the functor which comes from the hom of delta M into our V. So now just the straight up enriched yoneda lemma is going to tell us that we have V Rn. And this is all in E. Okay, so this is nothing special.
Yes, you fixed the little problem you had.
Yeah, everything's all aligned now. That's all that matters. Okay, so I'll probably end close to here. But, right, so what we have is this delta M, this representable is no longer like a T object. It lives outside of T objects. It is an enriched functor from delta M op into E. Whereas the V's that we want to look at, the V's are enriched monads. So in enriched monad-preserving functors, from delta M up into the monad T acting on E. So these are like two different levels. Nevertheless, I can take my my T object, the thing that I'm trying to turn into a T multicategory, and compare it against this because there's a forgetful functor. There's a forgetful functor that takes a monad and forgets that it's a monad and returns you just a category, the underlying category. So this is the underlying functor. And so what we're going to do is we're going to define our fibrations in the same way that we have, so fibrations meaning that we have like a solution to this lifting problem. We're going to define our lifting problem for T simplicial objects, which will define T infinity categories. Infinity T multicategories.
Nice.
All right. Okay. So like you said, we need our horns. We don't just we can't just do this with delta M. So we want to construct our horns. Let's see how I did this exactly.
No, it's we're going to go beyond the time that
Right.
YouTube. So let's just finish up. We'll,
Okay. So the point here is, and I'll skip the definition of the inner horns. We have a horn inclusion into our representables, and we can compare that to our proposed T object. So the things that satisfy this lifting property, they're called inner fibrant. And the idea is that the inner fibrant T simplicial objects are infinity T multicategories.
So to me, it looks like the one summary of this, so you take it, yeah, like you said, we do with your category thing and put multi everywhere.
Yeah, exactly. So, that introduces a bunch of problems, and I did actually skip like the real formal definition of this. I kind of just gave you a taste of it.
Well, and you also said, in addition, addition not just the formal definition, but the useful way of thinking of it.
Yeah, the formal and the useful, the well-defined way of thinking of this requires us to think of delta M as well as delta and delta plus, the other schemas I brought up, as shape categories. So I haven't found like a real brief catch line, like, I can write delta is, related to fin, the category of finite orders and order-preserving maps. So there's nothing as like streamlined as that, but there is a way to interpret these objects as certain shapes that encode the data of monads and higher cells.
Okay, so that's a nice way of thinking of at least of the object.
Yeah, exactly. And that gives us a lot of things.
Right, now presumably, obviously, when I said R to 1, I'm going to recover the original delta.
The original delta?
Well, the original thing, right? Isn't that just put R equal 1 because I have...
Oh, so R equals 1 is T? R equals 0 is ID.
Or 0, whatever,
Yeah,
that's special value, so.
Yeah, yeah, so there's a
Lisa
projection.
will obviously have that as a special case, the question is what is the more general?
Well, yeah, exactly.
In that case, it obviously comes with
So-
no.
So there's a functor from delta m down to
Right.
delta, and this will allow you to, like, you know, generalize or specify in either direction. Yeah, yeah.
No, as long as you say that special case of 0, well, we know there are the order preserving maps, it's just when it goes, you know, let's say, I guess you got this question, well, if it's equal 1, do I have any?
So what I'm trying to say is that the special case of 0, it isn't actually like simplicial sets because we don't
it is a
have
little
all the
different.
base maps.
Ah,
But if you take this and you project it down, which is what I'm drawing here,
Oh, okay.
you flatten all of this
Uh-huh.
down into one dimension, it becomes simplicial sets.
oh, I see, because you separated the two types of faces in your.
Yeah, yeah, exactly. Yeah.
Okay.
Yeah, thanks for the questions.
So one more question then. 'Cause
Yeah.
This has been very nice, and you've gotten us to a good spot.
Mm.
Is, so a property of, you know, infinity categories, quasi-categories, which are as infinity one categories, right, is that every higher cell, right, becomes invertible, right? That's now, if we've got T-multicategory that's got, these profs which have sort of these cells that are like the composition of path cells, right? Do we have a similar property that emerges here where there's going to be like, it's going to be actually an infinity one T-multicategory that some cell is going to become invertible above a certain level?
Yeah, okay. So to answer your question first, I want to distinguish between the two dimensions here.
Yeah.
So there is the morphism or the simplicial dimension,
Yep.
and this is what's going down,
Yep.
right? And it's also like the the third dimension into the board. And then there's the promorphism dimension. So the answer to the question is almost definitely yes in the simplex dimension,
Right.
but not in the promorphism.
Right, because in the promorphism dimension, right, those all exist even if we're in like a one T-multicategory.
Yeah.
And so obviously they're not going to get more invertible.
Yeah, you
But-
should think of these as edges in a graph,
Yeah.
not as morphisms, really, so, yeah.
But then, yeah, and so what you're saying, in this other dimension, we're gonna have that same property that's emerging, and I guess it's emerging from the composition law you just illustrated. The interfibrancy thing is gonna give us that property, right? That sort of these compositions are gonna be, you can compose and uncompose, and those can be like quasi-isos.
I should say you're talking about invertibility, and it's really, it's like,
It's going to end with 1.
it's hard, yeah, exactly. It's hard to define invertible cells because, you know, multi-categories only handle, like I said, n to 1. So to be invertible, we would need 1 to n.
Right.
And there actually are models for this. I think they're called polycategories. Now, I think that there's a whole, like this is you're opening up a little bit of a can of worms there.
Sorry. Yeah.
Like I think that there's a whole like spectrum of these delta m's in which like, say, like co-multicategories that go from 1 to n are on the spectrum. Multicategories, which is this one, is on the spectrum, and polycategories are somewhere in between.
Okay.
And then I don't know, like I think that there should be stuff in between all that as well, but I'm actually not that interested in solving that problem, but I think that it's the case. Yeah.
Oh, okay, yeah, but that's the other dimension that we're talking about.
Yeah.
Right, whereas we're just talking about like the other.
Yeah. Yeah, if
The
you
sort of-
wanted
the two
invertibility,
cells,
you
yeah.
need polycategories.
Yeah.
You can't do it in multicategories.
No, that's what I wanted to know. Great, thank you.
There are identities though, but yeah.
Wait, maybe you'll say, okay, the 1-to-1 guys are
Yeah,
invertible,
right. Yes.
and let's not worry about the n-to-1.
Yes. Yeah. But I think formally there's probably some problems with that. But anyway. Yeah. Yeah. Well, thanks for having me.
Thank you very much. Very nice. Beautiful. Thank you.